All right, so let's go ahead and do lesson 2 post-lab. This will take us about 20 minutes, 15, 20 minutes. And then our assignment tonight is worksheet number 1.
Yeah.
All right, so let's go ahead and get started. Okay, so what we're going to do today is summarize the findings and derive the Newton's second law. And we're going to just go ahead and try it and apply it to an example problem. And we'll be spending quite a bit of time on the second law. Okay, so those of you that did acceleration versus mass of the system. All right, I'm going to go ahead and put up some of your results so that we can take this. When you did, who was my massive system people? Any massive system people?
What is it?
That was with the sand, right?
That was, no. That was not with the sand. That was Shauna. Anybody else? You guys would have been the sand. Ethan, you guys would have been massive system. In other words, you're changing the total mass. You're adding mass to the top of the cart.
Yes.
That was you guys. Okay. So as you added mass to the top of the cart, you're going to hang on for a bit. I'm busy.
All right.
Probably 15, 20 minutes. When you added mass to the top of the cart, what happened to your acceleration? It decreased. All right, and that was inverse in nature. Let me show you the graph. Okay, let's see. Here's an example from a
Good. How are you?
All right. When we do this, here's an example from another class. And you can see the data is kind of spread out here. So in your notes, you want to have acceleration up here. Go ahead and sketch that in that first graph. Second graph, massive system. And what you get is you get a trend that curves down like this. Oh, you know, I'll get this in your notes. All right, like Shauna said, is that as the mass increases, what happens to your acceleration? It also goes down like so. Mathematically, what do we call that when you get a curve that's like this?
Parabola.
Specifically, it's called an inverse. It is a type of parabola, and it's specifically called an inverse curve. All right, so Shauna, do you remember what you did to straighten this? Do you remember what you tried?
We put like 1 over mass.
Huh? So they tried 1 over the mass down here. We're going to do that. And what they get is a straightened curve. You can see what it was, like so, and now it goes straight. Now, is it still inverse in nature? Yes, because we put an inverse on the bottom there. So on this next graph, make sure you sketch in Excel 1 over your mass, right? Gets you a linear fit like so. What this is saying is acceleration is proportional to the inverse of mass, like so. In other words, the more mass you add to your system, the less your acceleration is going to be. Now connect that with reality. Does anybody have an example of where it's more difficult, a situation that's more difficult to accelerate because you have more mass? Yeah, do you have an example?
So where you're showing mass on top of the cart, like where you're adding more mass to.
I'm gonna do that now.
Right, if you have more mass, again, but is there any, think outside the school setting than what we just did? You're right. You add mass to the top of the cart, it doesn't accelerate as quickly. Slower.
What was the question again?
Acceleration. What's a real life example of let's say, of this principle, that the more you increase the mass, the less the acceleration? Jake?
As William Shatner got older, he gained a lot of weight, so it was harder for him to accelerate while running.
That's true. Yes, there is that factor. Mass is definitely a factor in that. And there's probably some lung capacity. He may have been more in shape. Yeah, Jeff?
Adding more cars to the back of the train.
Yeah, you add more cars to the back of the train, the longer it's going to take to accelerate it. Yeah.
Semi-truck compared to a compact car.
Yeah, if you compare a semi's acceleration ability to a car's acceleration ability. And the other thing that it reverses on is deceleration. As a object with lots of speed or lots of mass, easier to slow down versus one that's less mass. Has anybody ever anybody ever drove with a trailer?
Yeah.
Okay, if you've ever driven a vehicle with a trailer and that thing has lots of mass on it, you try to stop, it doesn't slow down as quickly. You definitely feel it if you start hauling, if you ever get trucking or just ever have a load of timber in the back of your truck, anything like that. It's harder for your vehicle to accelerate. Some of those farm skills though are lacking in this non-FFA type of school. All right, let's go back to the PowerPoint. All right, so make sure you got those graphs sketched in there. Conclusion 2. Acceleration is proportional to the net force. So my net force people, that was the sand people. As you increased the mass hanging on the sand, what happened to the acceleration? Jeff?
It started to accelerate.
And went faster and faster. So the more you had hanging down from the hanging mass, the more it went, the faster and faster it went. Okay, so let's go ahead and take an example of this. They were directly proportional. Let me find a different example. Not a great example. There we go, there's a good correlation. So, so what we have there is we have acceleration on one side. We have net force down here. And we have a proportional. So acceleration is proportional to force net. So the more we put down the hanging, the more acceleration we had. Does anybody have a practical example of this? Anybody real life experience where they've had more force, there's more acceleration? Ethan?
You gave us the idea of a man attached to a boulder, and you throw the boulder and you fly right off.
Right, so now if you increase the boulder,
You're going to fly off.
you're going to go faster. You're going to accelerate faster, certainly. Okay, explain your jetpack analogy.
So the thrust of the jetpack.
Okay, so the bigger the thrust, the more acceleration you got. All right, Gage.
Fishing pole.
Okay, explain that.
The more weight you add towards the hook, the further and faster you go.
The more you can load. That's probably, yeah, it's a good example of that. As long as you don't go too much and you snap your pole. Snap plenty of poles in my life. Not necessarily doing that, but.
It's a big one.
Yeah, another example of this would be is pushing a cart in the grocery store. Not that you ever go shopping, but say you're buying groceries. You push it light, accelerates lightly. If you push it hard, accelerates light a bit more quickly. Right? So the harder you push, the more net force there is, the more acceleration there is. All right. So what I want you to get is a feel that these aren't just. This isn't lab. I want to take this out of the lab. I want you to start thinking about it in real life. These principles, because they'll make sense. They'll help you make more sense. All right. So here comes our equation. We're going to add to it. Actually, let me move this here. We're going to add to our equations the other forces. When we combine these two, we get Newton's second law. Newton's second law is this. A is proportional to force net, inversely proportional to mass. If you resolve this for a force net, you get force net is equal to m times A. Of course, I'm going to go ahead and define the variables. I strongly suggest you do this. Net force, m is mass, A acceleration. Okay, net force, units are newtons, mass is kilograms, acceleration is meters per second squared. So net force is the sum of the forces, and acceleration is always in the same direction as the net force. Yeah, Cameron?
So your second equation, the force net equals mass, is that times acceleration or minus acceleration?
Times. That's supposed to be a dot product. If you guys get that down in your notes.
Oh, Brady's famous studio.
All right.
Can you watch Brady?
Now let's talk about units here. We're going to get some funky units. Mass, its unit is kilogram. Acceleration is meters per second squared. So a newton, you're going with the unit, newton, that is a kilogram meters per second squared. Those two are interchangeable. If you broke down a newton, you can break it down into being a kilogram meters per second squared. All right, so according to this relationship, one newton is 1 kilogram meters per second squared. How is this similar to our force gravity equation from last unit? Does everybody remember it? It's Fg is equal to, what was the other two parts of that equation? M times something.
2 times.
It's real simple number. M times 10.
Oh,
Newtons per kilogram. Okay? How are these two similar? Both have an F. Very good.
Because 10 is the acceleration.
10 is your acceleration of what? When we drop, I didn't tell you guys this at the time, when I drop this object, how fast does it accelerate?
10 meters per kilogram.
10 meters per second squared. So check this out. If I use what I just learned about newtons, 10 Newton per kilogram. All right, let's take the Newton per kilogram part. So that's kilogram meter per second squared over by kilogram, and what are you left with?
Meters per second.
Meters per second squared. So a newton per kilogram is a unit of acceleration. So that's 10 meters per second squared. Basically, we just rework it's the same principle. When you're dropping an object by itself, like this paper clip or whatever, what's the net force on it? Nope, because it wouldn't be accelerated. The net force is 0. What's the only force acting on it when it's free falling?
Gravity.
Gravity. And so what's accelerated at? 10 meters per second squared. So see how we actually somewhat already derived it. We just derived it for its second time. But now it's going to be more universal than to just gravity by itself. Now, of course, if we hang this over a cliff and let it run off the edge of the cliff, it's not going to accelerate as much because only part of that net force is contributing. All right. What time do we have on that?
16 minutes.
Okay, go ahead and click it off and we'll go ahead and we'll finish up. All right. So the equations that you need to solve problems for these are essentially force gravity is equal to m times 10 newtons per kilogram. Force net is equal to m times a. And then you need the other definition of force net. Force net is the sum of all forces. Yeah, I'm going to be saying this day in and day out for the next week. You're going to get sick of it. I'm going to say it too many times. It's a mathematical thing. It's not just a words definition. It's a mathematical thing that comes from our force diagrams. Okay. So we got a 50-gram mass pulling a 500-gram cart as shown in a frictionless system, just like we did in our lab. What's the net force acting on the system, and what is the acceleration of the system? Now, let's go ahead and draw our simplified as if this is one full system together. Let's go ahead and draw our force diagram. So we've got force gravity on cart, force normal on cart, and again I distinguish those from this one right here, and we got force gravity on what? We'll call it on mass 1. Why did I draw that smaller? Because how much is this mass?
500.
500? How much is this mass?
50.
50. So which one's going to have a bigger force due to gravity? The cart. So I drew the other one proportionally smaller. Okay, it says, what is the net force acting on the system? So the net force is the sum of all forces. So if I add this plus that, what does it get me?
1,000.
0.
Oh, we're subtracting, sorry.
Yeah. So force normal on cart plus force gravity on cart gets us 0. Do they contribute to the net force of this system?
No.
No. So the net force of the system is equal to what?
10.
Now be careful here. Some people want to just say Fn. Don't be lazy. In the end, when these get way more difficult than this, that makes how you write this out is how your brain's going to do on these. So force net, notice I wrote the word net, is equal to which one of these is not being canceled?
Force gravity on mass 1.
Force gravity on mass 1. Okay. So, the question is, what is the net force? There's two ways that you can find net force. If you know the mass of that cart, which we do, and you know the acceleration, which, do we know the acceleration? Up here. No. So can we use this method to find force net?
No.
No. So we need to go to our next method. This one. So do we have an equation for Fg?
Yes.
Mass
M times 10. But it's of M1. So M1 times 10 newtons per kilogram is equal to our force net. Not always will force net equal your force gravity. That's why I'm going through this logic statement for later on. I could take 2 minutes and solve this problem and not explain what I'm thinking. I'm explaining what I'm thinking so that you pattern your thoughts after it. So that when you start these processes and go through it, you become very good at it very quick. Because you can model the way that you think based on what I think. Because I'm good at these. Alright, so mass 1. Now, some of you are going to make a mistake here. And I'm going to actually make it. Tell me what I did wrong here.
You didn't convert it to kilograms.
Oh, very good. You didn't convert it to kilograms. You must convert things to kilograms. Mr. Nevins, the other physics teacher, has a great method for doing that. As soon as he puts down the knowns and unknowns, he just goes ahead and converts it. And then you got cart, M of cart is 0.500 kilograms. So that when you go to grab it out of the problem, it's already converted. So we go ahead and solve that out. That's 0.5 newtons. So that's our answer for net force. Everybody good? Again, I said way more words than I needed to say. But again, I just took you through a process. There's only going to be one example like this on here, but believe me, in a week and a half from now, or a week from now when we go to quiz it, it'll be a lot more difficult to remember that. Okay, the next question is what's the acceleration? Alright, well here's our calculation. You can either look at your slope of velocity versus time graph, which we don't have. You can use any of your kinematics problems, which we'll do on quiz 2 stuff. Or you can use our equation, force net equals mass times acceleration. So we'll go ahead and do that for now. So, force net equals m times a. So we got 0.5. Now, here's probably arguably the most difficult point. The most difficult point in here is what mass do we use here? Should I say what mass?
One.
Which mass should I use? Yeah, Ethan?
Mass 1,
Why mass 1?
because that's the one that affects acceleration.
It is, but mass 1 is connected to what?
The string.
Cart.
Right.
Cart.
Cart.
Masses.
When we talk about this thing is not by itself. If this thing was by itself, it would go at 10 meters per second squared. Is it going to accelerate at a greater rate or less than that when it's attached to the cart?
Greater.
It's going to go at less.
Oh.
Right? If you attach yourself to a boulder and throw the boulder over the cliff, you're going to accelerate a lot less as if you just threw yourself over the cliff. Does that make sense? All right. When you do this, you want to use mass. Maybe I'll put that up here. Mass of system. Make a big note of that. Whatever, put it over here. Mass of system. Well, what's the total mass of the system? Those of you that did this part of the lab, how did you get the total mass? You put all of them on a scale, right? You put the cart and the string and the hanging mass all on there, and you found it. So in other words, you added them all together. So if we add all these together for mass of system, you get 0.550 kilograms. Times our acceleration. So now you just got to solve for A. Divide by both sides by 0.550. and that gets you 0.91. Just round it. Meters per second squared. So again, when you see me doing it, I think this happens a lot. You're like, oh, that's easy. Of course I make it look easy. I'm really good at it. It's like, what's a famous NBA player?
Michael Jordan.
Michael Jordan. It's like Michael Jordan and dunking, right? So he probably can't dunk anymore because his knees are blown out. But it's like Michael Jordan and dunking. You know, he makes it look easy, man. And then you get out in the driveway. You're like, oh yeah, here I go. You're like, oh. You don't even touch the net. You're like, oh. Why is it so easy? Because you saw the best doing it. That's the way it kind of is when you're going to start this worksheet. You're going to be like, wow, Mr. L, he's like the Michael Jordan of high school physics problems. You know what I'm saying? And then you're going to be like, oh, that's a whole lot harder than that. Or you'll get there, you'll be like, oh yeah, got the worksheet done, took me 2 minutes, yeah. And then you're going to look at it and you're going to be like, huh, boy, all the other groups are just entirely wrong. Or is it me? It's probably you.
It's like finishing your test before everyone else.
Yeah, that's a scary feeling. That's a bad feeling.
Great feeling. I still won't.
All right, in review, acceleration is proportional to the inverse of mass. Acceleration is proportional to net force. There's your equation. Net force is always the same exact direction as acceleration. And go ahead and start worksheet number 1, or turn your lab in if you haven't got it in. All right, thanks. Awesome, thanks, man.
Yeah, you're welcome.